There is an object built by human hands that is, right now, farther from Earth than anything else our species has ever made. It is not a massive ship, it is not a monumental construction. It is a small vehicle weighing roughly 722 kilograms, about the weight of a small motorcycle, with a gold-plated record on its hull and instruments designed in the 1970s. Its computer has less processing power than a basic calculator. Its transmitter operates at 22 watts, the power of a refrigerator light bulb. And yet, its signal still reaches Earth, and it is still moving away. Voyager 1 was launched on September 5, 1977. As of 2024, it is approximately 24 billion kilometers from Earth, about 160 astronomical units, 5 times farther than Neptune. In any direction you care to walk from our planet, 24 billion kilometers of empty interstellar space lies between us and it. It crossed the heliopause, the bubble of solar wind that encloses our solar system, in 2012. It is moving now through interstellar space, through the material between stars, through space that had never before been touched by anything made by people. And it is moving at roughly 17 kilometers per second, about 61,000 kilometers per hour relative to the Sun. This is fast by human standards. It is negligibly slow by astronomical ones. Tonight we are going to follow Voyager 1 forward in time. Not years, not centuries, billions of years, 1 trillion years. We are going to ask, honestly, carefully, without simplification, what will be happening to this small metal disk flying through the dark while the universe itself changes around it. And what we find will be one of the most astonishing thought journeys possible from our particular place in space and time. If the night is long, stay. Let us begin at the beginning, with the question of where exactly Voyager 1 is going and how long it will travel before anything happens. Voyager 1 is flying approximately in the direction of the constellation Ophiuchus, in a direction that, if you extend the vector of its motion far enough, points roughly toward the brightest stars in that region of sky. It is moving at roughly 35 degrees above the plane of the ecliptic, the plane in which the planets orbit, heading northward out of it. The first important question: will Voyager 1 ever pass close to another star? The answer is yes, but close in the astronomical sense and close in the human sense are very different things. Approximately 40,000 years from now, Voyager 1 will pass within roughly 1.7 light-years of a star called AC plus 793888, a red dwarf in the constellation Camelopardalis. This is not very close in a literal sense. 1.7 light-years is approximately 16 trillion kilometers. This is larger than the distance from our Sun to the nearest star, Proxima Centauri, at 4.24 light-years. This is not a close stellar flyby in the sense of a near approach. It is a passage within the same rough neighborhood. From Voyager's own perspective, this approach is indistinguishable from flying through empty interstellar space. The gravitational pull of AC plus 793888 will slightly deflect the spacecraft's trajectory by a negligibly small amount. But physically, nothing changes for Voyager. No heat, no illumination from a nearby star, no interaction. 40,000 years. Let us hold that scale in mind. 40,000 years ago, there were no agricultural civilizations on Earth. Homo sapiens had only recently reached Australia. Neanderthals were still living in Europe, or had only recently gone extinct. No written languages, no cities, no metal tools, no concepts of state or law. In 40,000 years, Voyager 1 will have travelled a distance equal to roughly 1/3 of the way to the nearest star. This is the first lesson about the scale of this journey. The speed of 17 kilometers per second, enormous by any human standard, is nevertheless negligible compared to the distances between stars. Interstellar space is so vast that even the fastest object ever launched by humans moves through it at a speed that appears stationary on any meaningful astronomical scale. Let us now talk about the timescales we will be examining, because the difference between 1,000 years and 1,000,000 years and 1,000,000,000 years and 1,000,000,000,000 years is enormous and requires special attention. 1,000 years. 1,000 years ago was 1024 CE. The Mongol Empire did not exist. The Renaissance had not happened. The Crusades had not yet begun. This seems long ago, and it is long ago in the sense of written human history. 1,000,000 years, 1,000 times longer. 1,000,000 years ago, Homo sapiens did not exist. Our ancestors were Homo erectus. The wheel was not invented. Fire was only beginning to be used regularly. 1,000,000,000 years. 1,000 times longer than 1,000,000. 1,000,000,000 years ago, there were no multicellular animals on Earth. The first multicellular organisms were only appearing. Oxygen in the atmosphere was still far less than today. 1,000,000,000,000 years, 1,000 times longer than 1,000,000,000. The current age of the universe is approximately 13.8 billion years. 1,000,000,000,000 years is roughly 72 times longer than the current age of the universe. It is a time so far in the future that most of the fundamental structures of the universe as we know them will have changed beyond recognition. This is the temporal horizon we are going to explore tonight. Let us begin with the near future, the first few thousand years. Over the next roughly 10,000 years, little changes physically for Voyager 1. It continues moving through interstellar space at nearly constant velocity. The Sun's gravitational influence on it is extremely weak at this distance. It continues to slow Voyager very slightly, but the effect diminishes as the distance increases. Over the next 10,000 years, Voyager will move another roughly 5.5 billion kilometers from the Sun, another approximately 37 astronomical units. The spacecraft itself will be electrically dead within this period. The radioisotope thermoelectric generators, RTGs, that power Voyager will by approximately 2025 be producing insufficient electricity to operate any scientific instruments. By roughly 2030, transmissions will likely cease entirely. Contact with Earth will be lost, forever. But the spacecraft body will continue moving. Metal does not disappear. Physical laws make no exceptions. Voyager 1 as a physical object, as a collection of atoms bound into certain structures, will continue its journey even when no electrical activity remains on it. By the year 10,000 CE, Voyager 1 will be approximately 300 astronomical units from the Sun. Sunlight at this distance is roughly 90,000 times weaker than at Earth. The Sun from this distance would appear as an exceptionally bright star, the brightest object in the sky, but already a point rather than a disk. The temperature of Voyager from solar heating would be close to absolute zero, roughly 4 Kelvin, since solar heat is completely negligible at such distances. It is interesting to think about what is happening to the gold-plated record, the golden record, attached to Voyager. Gold is extraordinarily resistant to chemical degradation. In interstellar space, there is no oxygen, no water, no chemically aggressive agents that could oxidize or dissolve the metal. The gold on the disk will remain in essentially pristine condition for enormous lengths of time. Physical damage from cosmic rays, high-energy particles pervading interstellar space, is the only significant degradation mechanism. These particles will slowly, atom by atom, damage the spacecraft's materials. But the rate of this process is negligibly small. Voyager will remain physically intact as an object for millions of years. Let us now talk about the key event occurring approximately 40,000 years from now, Voyager's passage past the star AC plus 793888. As we established, this will not be a close approach in any literal sense. 1.7 light-years is an enormous distance. But in the context of the galactic scale, it is the nearest stellar encounter Voyager will experience for the next several 100,000 years. AC plus 793888 is a red dwarf with a catalogue designation suggesting its position in the constellation Camelopardalis. It is a dim star that even professional astronomers rarely mention. It is interesting almost exclusively as the incidental nearest future neighbour of Voyager's trajectory. At the moment of Voyager's closest approach to this star, approximately 40,000 years from now, people will be living on Earth whose history and culture are as distant from our current civilization as the culture of 38,000 BCE is from us today. People of an era before agriculture, people just beginning settled ways of life. What will happen to humanity in 40,000 years? We absolutely cannot predict. Perhaps there will be nothing resembling our current civilization on Earth. Perhaps civilization will be so advanced that Voyager is detected and retrieved. Perhaps humans on Earth will be gone, either through extinction or because they have spread to other worlds. What will definitely happen? Voyager will pass within 1.7 light-years of a star that was not in its original navigation calculations. Because in 1977, nobody knew about AC plus 793888 as the nearest future star on the spacecraft's path. Let us now talk about what happens to Voyager itself over the next few 100,000 years, about the physical processes slowly changing the spacecraft. Interstellar space is not an absolute vacuum. It contains interstellar gas, primarily atomic hydrogen, with some helium and trace amounts of heavier elements, at a density of roughly 1 atom per cubic centimetre. This is 1 trillion times less dense than the air we breathe, but it is not zero. As Voyager moves through this gas, atoms collide with the spacecraft hull. At 17 kilometers per second, these collisions are rare, but each atom carries some kinetic energy. The cumulative effect over millions of years, slow surface erosion, is completely negligible on million-year timescales, but accumulates on longer ones. Cosmic rays, high-energy charged particles from deep space, primarily from supernova explosions and other energetic astrophysical events, continuously bombard the spacecraft. These particles pass through Voyager's materials, leaving ionization tracks and creating structural defects at the atomic level. Over time, this leads to embrittlement of metallic components. On timescales of a few 100,000 years, these processes have not yet destroyed the spacecraft. Metals remain structurally intact. The golden record retains its engravings. The antenna remains in place. Voyager will physically look roughly similar to today, tarnished, riddled with atomic-level defects from radiation, but recognizable as a human artifact. On timescales of tens of millions of years, the picture begins to change. Continuous cosmic ray bombardment gradually worsens the structural integrity of materials. Brittleness increases. Some of the thinner components, fine wires, thin plates, will begin to show signs of material fatigue. But the most significant destructive factor on long timescales is not chemical degradation, not radiation, and not collisions with gas atoms. It is possible collisions with larger objects. Interstellar space contains interstellar dust particles, tiny grains ranging from a few nanometers to a few microns in size, composed primarily of silicates, carbon, and ice. The density of these particles is very low, roughly 1 particle per cubic meter on average. But over millions and billions of years of travel, the cumulative impact of their collisions with Voyager becomes significant. At 17 kilometers per second, even a very small dust particle carries a certain kinetic energy. A particle 1 micron in size has a mass of roughly 10 to the minus 15 kilograms. At a collision speed of 17 kilometers per second, it carries kinetic energy of about 10 to the minus 7 joules, tiny by human standards, but sufficient to knock a few atoms from the spacecraft's surface. Over 1 billion years of travel, Voyager will pass through an enormous volume of interstellar space. The total mass of all dust particles it encounters will be very small, but each will gradually erode the surface. Thin outer layers of metal will slowly become thinner. More dangerous are occasional collisions with larger objects. Interstellar dust grains of a few hundred microns in size are far rarer but carry far more energy. A millimeter-sized particle moving in the opposite direction from Voyager at typical interstellar speeds could inflict meaningful mechanical damage to the spacecraft hull. However, the probability of such a collision over any given stretch of path is vanishingly small. Interstellar space is vast, and even the interstellar medium is surprisingly empty. The volume of space that Voyager crosses in 1 million years of motion, a huge cylinder the diameter of the spacecraft and several light years long, contains only a negligible number of particles larger than a dust grain. Let us now jump forward in time to a scale that begins to be truly astonishing, the first 1 million years. In 1 million years, Voyager 1 will be approximately 17 light-years from the Sun. At its current speed of 17 kilometers per second, it will have covered roughly 17 light-years in 1 million years, a good approximation though not exact because of gravitational interactions with stars it passes near. 17 light-years is beyond several of the nearest neighbours of our Sun. At 17 light-years lie stars like Tau Ceti, Epsilon Eridani, various red dwarfs. By this time, Voyager will be in the vicinity of entirely different stellar systems than the one it left. What is happening on Earth in 1 million years? This is an almost incomprehensible temporal horizon from the perspective of human history. All of recorded human history spans roughly 5,000 years. 1 million years is 200 times longer. This is longer than the distance from us to Homo erectus, the walking ancestor of humans. If humanity, or any form of its descendants, still exists in 1 million years, which is deeply uncertain, it will be something as different from us as we are from bacteria. Any direct cultural continuity with our current civilization would be extremely unlikely. Voyager itself in 1 million years. Metallic components survive. Radiation damage accumulates. The golden record is intact. Gold is extraordinarily resistant. The spacecraft is still recognizable as a human artifact, though perhaps somewhat tarnished and pitted by micrometeorite impacts. Notably, over this first 1 million years, Voyager will not pass close to any stellar system that might harbour habitable planets. Its trajectory passes through one of the more sparsely populated regions of our local stellar neighbourhood. It is moving away from the plane of the galaxy in a direction where stars are less densely distributed. This is another illustration of scale. In 1 million years, at a speed that staggers any earthly standard, Voyager is still travelling through ordinary interstellar space, without significant events, without close encounters, without interactions with other objects. Let us talk now about the first 10 million years, the timescale on which more significant changes begin to occur. In 10 million years, Voyager will have travelled approximately 170 light-years. This is already a significant distance within the galaxy, about 0.17% of the galactic disk diameter. Voyager will, by this time, be in a completely different stellar neighbourhood. No stars from its original surroundings will be nearby. They will all have moved to significant distances because of their own motions through the galaxy. On the 10 million year timescale, one important astrophysical process begins to matter: trajectory deflection from gravitational interactions with passing stars. As Voyager moves through interstellar space, every star it passes near exerts a small gravitational influence on its trajectory. No individual interaction is significant. Voyager passes too far from most stars to experience substantial gravitational pull. But over 10 million years, the accumulated effect of many such interactions gradually deflects the trajectory from its original direction. In 10 million years, the original direction of Voyager's motion, approximately toward the constellation Ophiuchus, will no longer accurately describe its current heading. Many small gravitational nudges from passing stars will have reoriented the trajectory in a random direction. This is important for understanding Voyager's fate on even longer timescales. After sufficient time, the direction of its motion becomes essentially random, the product of random gravitational scatterings from many stellar encounters. Voyager is no longer flying toward something specific. It simply drifts through the galaxy, its direction determined by the accumulated history of gravitational interactions. What is happening to the spacecraft itself in 10 million years? Radiation damage continues accumulating. Metallic components become progressively more brittle at the microscopic level. The crystalline lattices of metals are riddled with defects from cosmic rays. But the structural integrity of the spacecraft as a whole probably still holds. Voyager is still recognizable as an intact object. The golden record, one of the most durable components. Gold as a chemical element is inert in interstellar conditions. The engravings on the disk, numbers, diagrams, images, are preserved in the metal and require no active support. They degrade from the same radiation as the rest of the spacecraft, but gold is one of the most radiation-resistant metals. In 10 million years, the golden record probably still carries its information, somewhat tarnished, perhaps scratched by micrometeorites, but largely intact. Let us now talk about the 100 million year scale, and what begins to happen to the galaxy itself on this temporal horizon. In 100 million years, Voyager would have travelled approximately 1,700 light-years. This is already a meaningful fraction of the distance from our position to the edge of the galactic disk. Voyager will, by this time, be in a region of the galaxy that is currently 1,700 light-years away from us in its direction of travel. On the 100 million year timescale, effects begin to appear that are completely invisible on shorter timescales. First, galactic orbital motion. Our Sun moves in an orbit around the centre of the Milky Way at roughly 220 kilometers per second, with an orbital period of about 225 to 250 million years. Voyager, at the moment of its launch, inherited this same orbital velocity, 220 kilometers per second in the direction of the Sun's orbital motion, plus the additional 17 kilometers per second from the launch. So Voyager also moves in a galactic orbit, though somewhat different from the Sun's. In 100 million years, Voyager will have completed roughly 1/3 of one galactic orbit. Its position in the galaxy will be determined by the combination of its original momentum, the additional impulse from launch, and the accumulated gravitational scatterings from passing stars. Second, trajectory randomization. In 100 million years, Voyager will have experienced an enormous number of gravitational interactions with passing stars. The accumulated effect of these interactions has fully randomized the direction of its motion. It is now completely unrelated to its original launch direction in 1977. Third, at the 100 million year scale, collisions with interstellar clouds become meaningful. The galaxy contains molecular clouds, dense concentrations of cold gas and dust in which stars form. Voyager will cross several such clouds in 100 million years. Inside a molecular cloud, the gas density is significantly higher than in open interstellar space, from a few hundred to a few thousand molecules per cubic centimetre rather than one. This does not stop Voyager, but increases the rate of micrometeorite impacts and surface erosion. What is happening to the spacecraft in 100 million years? Some of Voyager's materials will probably begin showing overt signs of structural degradation. Thin metallic components, wires, brackets, may have become brittle enough from radiation damage that vibrations from micrometeorite impacts begin breaking them. But the main hull, the thicker aluminium and titanium structural elements, probably retains structural integrity. Voyager, in 100 million years, will likely look like a severely damaged object with broken, protruding elements, but still identifiable as an artificial artifact by any technologically advanced observer. The golden record is probably still intact, perhaps with some surface damage from micrometeorites, but physically still attached to the spacecraft and carrying a significant portion of its original information. Let us now talk about the 1 billion year scale, the temporal horizon at which fundamental changes occur not just to Voyager itself, but to the solar system it left behind. In 1 billion years, Voyager 1 will have travelled approximately 17,000 light-years. This is a significant fraction of the galaxy, about 17% of the galactic disk diameter. Voyager will be in a completely different region of the Milky Way, its trajectory long since fully randomized by gravitational scatterings. What is happening to Earth and the solar system in 1 billion years? The Sun in 1 billion years will be roughly 10% brighter than it is now. This seems like a modest change, but its effects on Earth will be significant. A brighter Sun means a higher average surface temperature on Earth. In roughly 500 million to 1 billion years, the temperature on Earth may rise enough that liquid water on the surface becomes unstable. This is not a sudden catastrophe. It is a slow, gradual process, temperature rising by a few degrees over hundreds of millions of years. But in 1 billion years, Earth will probably be significantly warmer than now. Complex life as we know it may be impossible on the surface. What is Voyager doing in 1 billion years? Here we approach the physical limits of the spacecraft's durability as a unified object. Over 1 billion years, radiation damage to materials will be truly significant. The crystalline lattices of metals will be riddled with an enormous number of defects. Some metallic components may have become so brittle they break apart from any mechanical disturbance. But it is critically important to understand what happens to Voyager as a collection of atoms. Atoms are not destroyed by radiation damage. They do not disappear. They simply move from correct positions in a crystalline lattice to defective positions. Metal remains metal. Gold remains gold. What degrades is the structural organization. Wires break. Brackets fail, components detach from the hull and drift in space in the immediate vicinity of the main body, forming a tiny cloud of debris moving in roughly the same direction as the main hull, because their velocities are still very close to the original. In 1 billion years, Voyager probably exists as a cloud of fragments, some large, some tiny, travelling roughly together. The golden record may have detached from the main hull, but is moving nearby. The antenna is likely broken or separated. The overall shape of the spacecraft is unrecognizable compared to the original. But the atoms, every aluminium atom in Voyager's hull, every gold atom in the Golden Record, every plutonium decay product in the RTG, all of them are still here. The journey continues, not as a single spacecraft, but as a dispersed cloud of atoms and fragments, still bound by their common history, still, in some sense, Voyager 1. Let us now talk about the 4 to 5 billion year scale, the moment when one of the greatest events in the history of our galaxy and nearest cosmic neighbourhood will occur. In roughly 4.5 billion years, the Milky Way and the Andromeda Galaxy will begin their merger. This will not resemble two solid objects colliding. It will be a slow, gradual interpenetration of two galactic systems. Most individual stars will not collide. Stars within galaxies are separated by enormous distances, and the probability of any two specific stars literally colliding is negligibly small. But the gravitational interactions will be enormous in scale. The orbits of stars in both galaxies will be radically disrupted. Some stars will be ejected from the galactic system entirely, thrown out at hyperspeeds into intergalactic space. Others will be captured into entirely new orbits in the merging structure. At roughly the same time, approximately 5 billion years from now, the Sun will begin expanding into a red giant. Its outer layers will swell beyond the current orbit of Mars, possibly even beyond Earth's orbit. Earth, if it still exists as a planet, will either be swallowed by the expanding solar envelope or be radically transformed into a lifeless, melted rock. What is happening to Voyager at this time? In 4.5 billion years, Voyager is so far from the Sun, roughly 75,000 light-years, halfway across the entire galaxy, that events in the solar system have absolutely no effect on its fate. The Sun becoming a red giant, the merger with Andromeda, any catastrophes in the home system, all of this happens so far away that Voyager experiences no direct effects. Voyager at this time is a cloud of atoms and subfragments travelling roughly together through the space of the merging galaxy of Milkomeda, as the future combined galaxy is informally called. Its trajectory was fully randomized long ago. It is not moving toward or away from anything. It simply drifts, slowly by galactic standards, incomprehensibly fast by human ones, through the gravitational chaos of two merging galaxies. Let us now talk about a timescale far larger, the scale of tens of billions of years, at which events occur that define the long-term fate of the universe itself. In roughly 100 billion years, 7 times the current age of the universe, the structure of the universe will begin changing substantially. Dark energy continues accelerating the expansion of the universe. The most distant galaxies, already receding from us at speeds exceeding the speed of light due to the expansion of space itself, will be even further away and even more unreachable. In tens of billions of years, more and more galaxies will cross the Hubble horizon, the distance beyond which their recession speed exceeds the speed of light, and disappear from the observable universe forever. By 100 billion years, the local group of galaxies, to which the Milky Way and Andromeda belong, by this time long since merged into a single aging elliptical galaxy, will be an island isolated in an increasingly empty observable space. Neighbouring galaxy groups and clusters will have departed beyond the observability horizon. The universe, from the perspective of any observer in our galaxy, will look increasingly empty. Not because galaxies physically disappear, but because they recede faster than light can reach us. New stars in the galaxy cease forming in roughly a few trillion years, when the interstellar gas is exhausted after many generations of star formation. But existing small stars, red dwarfs, live inconceivably long. A red dwarf a few times the mass of Proxima Centauri burns its hydrogen so slowly it continues shining for trillions of years. What is happening to Voyager on the 100 billion year scale? By this time, Voyager, or what remains of it, is somewhere in the combined galaxy descended from the Milky Way and Andromeda. Its trajectory was fully determined by the history of gravitational interactions with thousands of stars it passed near over these billions of years. It may be anywhere in this galaxy, perhaps in the central regions, perhaps on the far periphery, perhaps ejected into intergalactic space by a particularly violent gravitational scattering. The atoms composing Voyager are still present, still travelling. Let us now talk about the 1 trillion year scale, the temporal horizon that is the destination of tonight's journey. 1 trillion years is 10 to the 12th power years. The current age of the universe is approximately 1.38 times 10 to the 10th power years. A trillion years is 72 times longer than the current age of the universe. This is not just the very distant future. It is a future so distant that most of the fundamental astrophysical structures that exist now will have ceased to exist long before this moment. In 1 trillion years, all stars except the smallest red dwarfs have long been dead. Sun-like stars live about 10 billion years. The most massive stars, a few million years. Even red dwarfs, several times more massive than Proxima Centauri, will have exhausted their fuel long before a trillion years. The smallest red dwarfs, objects with roughly 8 to 10% of the Sun's mass, have main sequence lifetimes of the order of 10 trillion years. In 1 trillion years, the smallest red dwarfs are still shining, though dimming as their hydrogen fuel is depleted. New star formation ceased trillions of years ago. The interstellar gas is exhausted. The galaxy by this time is populated primarily by stellar remnants, white dwarfs, neutron stars, black holes, and the few remaining small red dwarfs. Dark energy continues driving the expansion of space. The observable universe for any hypothetical observer in our galaxy is almost completely empty. Almost all other galaxies have gone beyond the horizon. Only the local group, now a single aging elliptical galaxy, is visible as an island in space, filled with background radiation from the cosmic microwave background, shifted to extraordinarily long wavelengths. What is happening to Voyager in 1 trillion years? In 1 trillion years, Voyager, if no catastrophic collisions have occurred, has travelled a distance of roughly 17 million light-years. This is significantly larger than the diameter of our local group of galaxies, approximately 10 million light-years. This means that with sufficiently lucky or unlucky gravitational scatterings, Voyager by this time could have been ejected far beyond the local group into intergalactic space. Intergalactic space is truly almost absolute vacuum. The density of matter in intergalactic space is roughly 1 atom per 10 cubic meters. This is 10 times less dense than the interstellar medium in our galaxy. The rate of collisions with dust particles drops even lower. The rate of radiation damage from galactic cosmic rays is also lower, though still non-zero. If Voyager has reached intergalactic space, it now drifts in truly boundless emptiness. No stars nearby, no galaxies within reach, nothing but a very faint stream of photons from the dying galaxy it left behind. The atoms it is made of, still here, still moving, but are they still Voyager? Physically, possibly not. In 1 trillion years, even the most robust metallic structures have probably fragmented into individual chunks. The golden record has perhaps broken into a cloud of gold atoms and small fragments. Atoms from different parts of the spacecraft have separated by small distances, a few meters, perhaps a few kilometers, from various gravitational scatterings and random impulses from micrometeorite impacts. But in some more abstract sense, still yes. The atoms that were once Voyager 1 continue their journey. They carry in their nuclear structure evidence of their origin, isotopic ratios indicating they formed in our solar system, some processed in the nuclear reactor of the RTG, some bearing traces of radiation damage accumulated over 1 trillion years of travel. The atoms will outlast the message they once carried. In 1 trillion years, somewhere in the vastness of this cooling, darkening, emptying universe, 17 million light-years from where the sun used to be, atoms drift. Atoms of aluminum and gold and platinum and titanium, perhaps separated by light-years from each other, carrying in their nuclear structures isotopic signatures saying they were created in a specific star system, carrying traces of radiation damage accumulated over 1 trillion years of travel. These atoms never stopped, never, since September 5th, 1977, have they ceased moving. They pass through the heliosphere, through interstellar space, probably through intergalactic space, through a universe in which their home star burned out long ago, their home planet was destroyed long ago, their makers long ago, by billions of years, became part of a history that no one remains to remember. And they are still moving. The law of conservation of momentum is absolute. In interstellar and intergalactic space, there are essentially no forces capable of stopping them. They will move as long as the universe exists in a form that allows motion to have meaning. This is what people did in 1977. In the middle of the Cold War, with computers less powerful than a basic calculator, with chemical fuel rockets, they launched something that will outlast their civilization, their species, their planet, their star. Not because they planned a trillion-year journey, because they understood the law of conservation of momentum and applied it. A small piece of physical reality that will forever carry the evidence that once, in an incomprehensibly distant past relative to any future vantage point, something here existed that was capable of thinking, building, launching. Look at the sky one more time before going inside. Somewhere in that darkness, right now, in this second, it is flying. And in 1 trillion years, it still will be. Let us talk about something we touched on but did not examine in full depth, about what happens to the atoms of Voyager at the subatomic level on timescales of billions and trillions of years, because the story of its journey on these scales is largely determined by atomic and nuclear physics. An aluminium atom, the primary material of Voyager's hull, consists of a nucleus with 13 protons and 14 neutrons, surrounded by 13 electrons. Stable aluminium-27 has no radioactive isotopes with a sufficiently long half-life to be significant on billion-year timescales. The aluminium-27 nucleus is stable. It will not spontaneously decay without external influence. However, external influences occur continuously. When a high-energy proton or heavy ion from galactic cosmic rays collides with an aluminium-27 nucleus, a nuclear reaction occurs. The result depends on the collision energy. At sufficiently high energies, the nucleus can shatter, a process called spallation. From one aluminium atom, several atoms of lighter elements can form: magnesium, sodium, neon, or lighter fragments. This process is slow on human timescales, but significant over billions of years. In 1 billion years, a meaningful fraction, perhaps a few percent, of the aluminium atoms in Voyager's hull will have been transformed into other elements through spallation. Voyager's hull, after 1 billion years, will not be pure aluminium. It will be a mixture of elements formed from nuclear reactions. This is a physical process changing the very chemical identity of the spacecraft. Not just structural destruction, a transformation of matter itself. Atoms that were aluminium become magnesium, sodium, neon. Gold is more resistant to spallation than aluminium. Its nuclei are heavier and require higher energy to break apart. But over sufficient time, billions of years, even the gold atoms of the golden record will undergo nuclear transformations from high-energy collisions. The plutonium-238 in Voyager's RTG is already undergoing radioactive decay. This is what produces heat and electricity. The half-life of plutonium-238 is 87.7 years. Within a few thousand years, all the plutonium-238 in the RTG will have transformed into uranium-234 through a chain of alpha decays. Uranium-234 is itself radioactive with a half-life of about 245,000 years. Over millions of years, it will transform into thorium-230, then radium-226, then radon-222, lead-206, and other products of the uranium decay chain. By the time Voyager approaches the nearest star, about 40,000 years from now, its RTG will contain no plutonium. There will be uranium-234 and the initial products of its decay. In 1 million years, there will be a mixture of isotopes still evolving along the radioactive decay chain. This adds another layer to Voyager's story. Not only does its structure degrade, its chemical and isotopic composition continuously changes, slowly, atom by atom, through radioactive decay and nuclear reactions caused by cosmic rays. Let us now talk about the specific number that makes the trillion-year journey particularly astonishing. Voyager 1 moves at roughly 17 kilometers per second, 61,000 kilometers per hour. Since launch, it has covered about 24 billion kilometers. A trillion years is roughly 21 billion Voyager lifetimes. Each Voyager lifetime is 47 years. If every moment since launch had passed 21 billion times in succession, we would have traversed a trillion years. The distance travelled in a trillion years of the current speed, approximately 17 million light years as we calculated. This is the distance from the Milky Way to the nearest galaxies comprising our local group, the Andromeda Galaxy, the Triangulum Galaxy, dozens of dwarf galaxies. If Voyager could travel in a straight line toward Andromeda, which it cannot because its direction will be repeatedly altered by gravitational scatterings, it would have covered the distance from our galaxy to Andromeda and another 7 million light-years beyond in 1 trillion years. In 1 trillion years, Voyager will have travelled farther than the distance from our galaxy to Andromeda. This does not become less astonishing through repetition. A small spacecraft, launched by a chemical rocket, moving at a speed that seems negligible by astronomical standards, given sufficient time, will cover distances that define the scale of our local group of galaxies. Time changes everything. Sufficient time changes everything. Let us now talk about what is perhaps the most beautiful mathematical fact about Voyager's journey, about the connection between its speed and the structure of the universe. Voyager 1 moves at about 17 kilometers per second. This is about 0.0057% of the speed of light. For any practical calculation, for travel to neighbouring stars, for movement across the galaxy, this speed is negligible. But the universe is expanding. According to Hubble's law, the recession velocity of an object from us is proportional to its distance. The Hubble constant is currently about 67 to 73 kilometers per second per megaparsec. This means that an object at a distance of 1 megaparsec, about 3.26 million light-years, is receding from us at about 70 kilometers per second. Voyager's speed, 17 kilometers per second, is comparable to the recession speed of an object at a distance of about 0.24 megaparsecs. That is roughly 800,000 light-years. If Voyager ends up in intergalactic space more than 800,000 light-years from the nearest galactic structure, which may happen over many billions of years if it is ejected beyond the local group, then the expansion speed of space at that distance begins to compete with its own speed of motion through space. If Voyager is far enough beyond the local group, the expansion of space will push it away from galactic structures faster than its own motion can overcome. It will be in a position where even if it could somehow turn around, which is physically impossible since it has no engines, it could not do so against the current of expanding space. This means there is a critical distance beyond which Voyager, or any other object, becomes irreversibly cut off from our galactic family. This distance is called the Hubble sphere, or the Hubble horizon. Beyond this distance, the recession speed exceeds the speed of light. But Voyager's speed through space, as distinct from the recession speed, which is a property of expanding space rather than motion through space, remains 17 kilometers per second. An object can cross the Hubble horizon if it is far enough from us. This does not violate special relativity because the expansion of space itself is not constrained by the speed of light. This adds yet another level to Voyager's fate. Over sufficient time, with sufficiently favourable gravitational scatterings ejecting it beyond the local group, Voyager may end up in space that is literally expanding faster than it moves through it. In this case, its atoms will be forever carried by the expansion of the universe into regions that can never again interact with the local group or any other galactic structure. This is absolute solitude, not just very far from home, physically cut off from everything. In space, that itself carries it ever farther, not because it is moving, but because the space between it and everything else is literally stretching. Let us now talk about what this means for the concept of distance. On human scales, distance is measured in kilometers. On solar system scales, in astronomical units. On stellar scales, in light years. On galactic scales, in kiloparsecs. On cosmological scales, in megaparsecs. Voyager 1 began its journey measured in terrestrial kilometers. Now it is measured in astronomical units. In thousands of years, in fractions of light years. In millions, in light years. In billions, in thousands of light years. In trillions, in millions of light years. Every unit of measurement humanity invented for measuring large distances will successively apply to Voyager as it moves through time. This is a journey not only through space, but through the scale registers of our understanding of the universe. Voyager began in the same scale as our everyday life and will wander through all scales up to the cosmological. Let us now talk about what specifically the Golden Record represents on the trillion-year timescale, because it adds a dimension to this story that no purely physical account can fully capture. The Golden Record was designed and assembled by a team led by Carl Sagan. It contains 116 images of Earth and life on it. Sounds, rain, surf, wind, crickets, frogs, birds, whales, a baby crying, a mother speaking, footsteps. Music spanning cultures and centuries, Bach, Chuck Berry, Peruvian panpipes, Azerbaijani folk songs, Indian classical music, Blind Willie Johnson, Beethoven. Greetings in 55 languages. A message from the Secretary-General of the United Nations. All of this travels now in interstellar space. The cry of a baby, the sound of rain on leaves, a snippet of bark played on an organ. All of it encoded in grooves on a gold disc flying through darkness 160 astronomical units from Earth. That baby belonged to someone specific. Those birds lived or are living somewhere specific. That rain fell on specific trees in a specific forest on a specific day. All of them have long since become part of the past, but the record of their existence, the physical trace in the form of grooves in a gold disc, continues moving in the darkness. In 1 trillion years, through a time in which neither the trees, nor the birds, nor the babies, nor the planet on which they lived, nor the star that warmed them still exist, these grooves, if the disc has survived as a single object, still carry this message, a message that no one will read, a message that will probably never reach any recipient, but a message that continues the journey. There is something deeply moving in this if you allow yourself to sit with it. The first human message to other civilizations, sent with almost no hope it would be received, has been travelling for almost 50 years. It will travel for another 1,000,000 years, another billion, possibly another trillion. No person who wrote those greeting words, no scientist who selected those sounds, no engineer who built that disc, none of them will see the end of this journey. None of us will. No human being will ever know where exactly this journey ends, or whether it ends at all. And yet the journey continues. This is perhaps the most accurate description of what our species is at this stage of its existence. Beings capable of sending messages into the dark, not knowing where they fly, not knowing whether they will be received, not knowing whether anyone will exist long enough to learn the outcome, capable of a gesture that exceeds any practical purpose, a gesture made because the very idea of sending a message seems meaningful regardless of the probability of its receipt. Let us now talk about one aspect of Voyager's journey that connects the physical story we have been building to the human story beneath it, about the specific people who have spent their professional lives associated with this mission. Voyager 1 has been in continuous operation longer than many of the engineers who now work with it have been alive. Some people who contributed to the Galileo mission's Europa discoveries began that work before some of their graduate students were born. The same is true of Voyager. Careers that began at JPL in the 1970s, when the spacecraft was being built, have spanned to careers now ending or already ended with the spacecraft still active. The communication delay that currently stands at about 22 hours one way, sending a command and waiting 22 hours to know if it was received and executed, makes every interaction with Voyager a study in patience. A question sent now receives its answer tomorrow. A problem detected today cannot receive a response until tomorrow. Every decision about what to tell Voyager to do must be carefully thought out in advance, because there is no opportunity for rapid correction. This communication regime, which will only have been experienced during the operational life of the Voyager spacecraft, is itself a kind of preview of what any genuine interstellar relationship would involve. Not hours of delay, but years. Not questions answered the next day, but questions answered in the next decade. The impossibility of real-time interaction scaled up to the point where it becomes a defining feature of any possible engagement. Voyager is a very early and very modest rehearsal for this future. The 2023 to 2024 episode, when Voyager's Flight Data System computer began sending garbled data, illustrated both the difficulty and the achievement of working at this distance. Engineers at JPL received data that made no sense. They diagnosed the problem by process of elimination, sending commands and waiting 44 hours for each round-trip response to confirm or deny each hypothesis. They identified a damaged memory chip. They relocated the relevant code to working sections of memory, a technically demanding operation at any distance, astonishing at a distance of 22 billion kilometers with 1970s-era computer architecture. And they succeeded. Voyager resumed normal operations. This represents something important about human capability and human commitment. Not just that the engineering is impressive, though it is, but that people chose to invest the effort, that the scientific value of maintaining contact with the first interstellar probe justified months of careful, patient, technically demanding work to diagnose and fix a problem on a spacecraft nearly 50 years old in the darkness of interstellar space. Let us now talk about one more thing, about the specific experience that is possible right now, tonight, that will not always be possible. Right now, Voyager 1 is transmitting. Its 22-watt transmitter is sending a signal through 24 billion kilometers of space. That signal is arriving at the 70-meter dishes of the Deep Space Network in Goldstone, California, in Madrid, Spain, in Canberra, Australia. Engineers are receiving it. Data is being decoded. Scientific measurements of the interstellar medium are being recorded. This is happening, not as an abstraction, as a physical process occurring right now. In a few years, it will stop. The RTGs will produce insufficient power. The transmitter will go silent. The contact will end. After that, we will know Voyager continues moving. Physics guarantees it. But we will no longer hear what it measures. We will no longer receive data from the first human object in interstellar space. This window, the extraordinary historical window in which humanity has a functioning scientific instrument in interstellar space returning real-time data, is closing. It will not reopen until another mission is planned, funded, built, launched, and reaches interstellar space. There is no such mission currently approved. The planning horizon for a purpose-built interstellar probe is decades. This means the people working with Voyager right now are doing something no previous generation could do and no following generation, for perhaps decades, will be able to do. They are communicating with an instrument in interstellar space. They are receiving measurements of a medium no human instrument has ever sampled before. Every day that contact continues is irreplaceable. This is the specific character of the present moment in Voyager's story. Not the past, when it was launched and performed its planetary encounters. Not the trillion-year future when its atoms drift through intergalactic space, but right now, these few remaining years when it still transmits. We are in them. Let us now talk about what the trillion-year journey of Voyager says about something broader, about the permanence of the past and the nature of cause and effect in a physical universe. Everything that has ever happened leaves a trace in the physical state of the universe. A sound wave eventually dissipates, but the energy it carried goes somewhere, transferred into heat, into the motion of molecules, into the universe's entropy. A light pulse travels outward at the speed of light, carrying information about the event that created it. A physical object moves through space, carrying in its momentum the complete history of every force that was ever applied to it. Voyager 1 carries in its current momentum the integrated effect of every rocket burn that launched it, every gravitational assist from every planet it visited, every tiny gravitational tug from every asteroid it passed near, every photon of radiation pressure that has acted on its surface for nearly 5 decades. This momentum is a physical record of Voyager's complete history. In principle, if you could measure its current position and velocity with infinite precision, you could reconstruct every event in its past. The gravitational assists are encoded in the current trajectory. The original launch burn is encoded in it. Every interaction is there, summed up, integrated. The universe, in this sense, does not forget. Physical information is encoded in the state of matter and energy. Voyager's existence, its specific journey through specific positions at specific velocities, is recorded in the physical state of the universe to a degree that, in principle, can never be entirely erased without violating the fundamental laws of physics. The specific atoms that compose Voyager carry isotopic signatures of their origin. They carry radiation damage signatures of their journey. They carry the mechanical stress history of their structure. All of this is information, physically encoded, physically real. In 1 trillion years, when those atoms are scattered across light years of intergalactic space, each one of them still carries this information in its nuclear and atomic structure. Not readable, not accessible, but physically present. The universe has not forgotten Voyager. It has simply dispersed the record of its existence across an unimaginable volume of space. This is one of the most profound implications of physical law applied to a human artifact on cosmological timescales. The past is permanent. Not in the sense that we can access it, but in the sense that its consequences never fully disappear. Every event that has ever happened is still encoded somewhere in the physical state of something. Voyager 1 is a particularly clear illustration of this because its physical trace, its atoms, continues to move through space in a direction and at a speed that reflects its complete history. The movement is the memory. Let us now talk about what it means that Voyager will outlast almost everything we know. In the order of things that will end, consider what Voyager outlasts. Human beings alive today will die in decades. This is universal and certain. The civilization that launched Voyager, whether we think of it as American or Western or technological or any other category, will not persist in recognizable form for more than centuries to millennia. No civilization in history has persisted in recognizable form for more than a few thousand years. The species Homo sapiens will almost certainly not exist in its current biological form for more than a few million years. The average longevity of a mammalian species in the fossil record is roughly 1 to 2 million years. Whether we transform ourselves through technology or evolution into something different, or go extinct, or both, the specific biological form of humanity is temporary on geological timescales. Earth will be transformed beyond recognizability. First by continued biological and geological evolution, then by the brightening of the sun in 1 billion years, then by the sun's red giant phase in 5 billion years, and ultimately either swallowed or left as a barren cinder. The sun will exhaust its hydrogen fuel in about 5 billion years, expand into a red giant, shed its outer layers as a planetary nebula, and leave behind a white dwarf that will cool for trillions of years before becoming a black dwarf, a cold, dark remnant. The Milky Way as we know it will merge with Andromeda in about 4 to 5 billion years, ceasing to exist as a distinct galaxy and becoming part of Milkomeda. Almost all stars in the resulting galaxy will be dead in a few trillion years. Through all of this, through the death of humans, the end of civilization, the extinction or transformation of species, the end of Earth, the death of the sun, the transformation of the galaxy, Voyager's atoms continue moving. They will not be present at the end of stars. They will be past stars entirely, 17 million light-years from where they started. They will not witness the death of the sun. They will be 75,000 light-years away when the sun dies. They will simply continue, moving, through an increasingly dark, increasingly cold, increasingly empty universe, until something stops them. And in interstellar or intergalactic space, there is essentially nothing to stop them for any timescale we can meaningfully calculate. This outlasting of almost everything is not a metaphor or a poetic construction. It is a direct physical consequence of the law of conservation of momentum applied to an object in nearly empty space. The same law that operates in every physics classroom, in every engineering calculation, in every rocket launch. Understanding this law and applying it in 1977 produced something that will outlast the civilization that understood it. This is perhaps the most tangible illustration available of the difference between knowledge of physical law and the transience of the civilization that possesses that knowledge. The knowledge is encoded in the movement. The movement continues after the knowledge's possessors are gone. This is what Voyager 1 represents at the trillion-year scale. Not a spacecraft, not a scientific instrument, not even a message to other civilizations, though it carries one. It is the physical embodiment of the fact that on a specific small planet orbiting an ordinary star in a spiral arm of an ordinary galaxy, at a particular moment in cosmic time, beings capable of understanding physical reality existed and left a trace that will persist long after everything else associated with them is gone. Let us talk about something that connects Voyager's physical journey to the deeper question of what information actually is in a physical universe, because this question becomes unusually concrete when applied to an artifact traveling through space for 1 trillion years. Information, in the physical sense, is a pattern. It is the difference between one arrangement of matter and another. The text on this page is information because the arrangement of ink differs from what would be there if nothing had been written. The grooves of the golden record are information because they are different from what the surface would look like if nothing had been engraved. All physical information is encoded in physical states of matter and energy, and all physical states of matter change over time, through thermal fluctuations, through radiation damage, through chemical reactions, through mechanical disturbance. This means physical information is not permanent, it degrades. The rate of degradation depends on the stability of the medium and the harshness of the environment. The golden record in interstellar space is perhaps the most durable medium for information storage ever created by human hands. Gold is chemically inert in vacuum. The grooves are physical rather than magnetic or electronic. They do not require any active process to maintain. The information is literally carved into one of the most chemically stable materials known. And yet it will not last forever. The cosmic ray bombardment that slowly damages the metal structure will eventually erode the grooves beyond readability. The occasional micrometeorite impact that scours a patch of the surface will destroy whatever information was in that patch. Over sufficient time, the record of sounds and images and greetings encoded in those grooves will degrade to noise. Estimates vary. Some analyses suggest the surface of the golden record will be significantly damaged within a few 100 million years from accumulated radiation and micrometeorite impacts. Others are more optimistic. A few billion years under the relatively gentle conditions of interstellar space. But on trillion-year timescales, the information is almost certainly gone. What remains? The atoms. The gold atoms that were the carrier medium for the information persist long after the information they encoded has been erased. The message degrades. The medium outlasts the message. This inversion of what we normally expect is one of the most striking facts about information on cosmological timescales. We tend to think of the message, the meaning, the content, as the important thing, and the medium as incidental. But physically, the medium is more durable. The atoms of the messenger outlast the message. In 1 trillion years, somewhere in intergalactic space, there are gold atoms. They do not carry the sounds of Earth. They do not carry the images. They do not carry the greetings. The grooves that encoded those things were erased billions of years ago by the accumulated damage of a trillion-year journey. But those gold atoms were once part of something that carried all of those things. and they carry in their nuclear structure the isotopic signature of their origin in a solar nebula around a specific star. And they carry the damage signature of 1 trillion years of cosmic ray bombardment. These are not the message that was intended, but they are a physical record of a physical history. The universe keeps a different kind of record than the one we intended to leave. Let us now talk about one of the most underappreciated aspects of Voyager's mission. The fact that both Voyager spacecraft together constitute an experiment in comparative interstellar medium sampling that has no precedent. Voyager 1 crossed the heliopause heading north, roughly 35 degrees above the ecliptic plane, at approximately 122 astronomical units in August 2012. Voyager 2 crossed the heliopause heading south, roughly 35 degrees below the ecliptic plane, at approximately 119 astronomical units in November 2018. These two entry points into interstellar space are in nearly opposite directions relative to the ecliptic. They are separated by a physical distance of roughly 150 to 200 astronomical units, depending on exact geometry, about 2 to 3 times the distance from Earth to Pluto. The properties of the interstellar medium measured by the two spacecraft at these 2 points were not identical. The heliosheath, the region between the termination shock and the heliopause, appeared different in the 2 directions. The heliopause itself appeared thicker and less distinct in the direction Voyager 1 crossed compared to the direction Voyager 2 crossed. The plasma temperature just outside the heliopause was measured differently by the two spacecraft. The magnetic field orientation at the crossing differed subtly. This is the first stereoscopic view of the heliospheric boundary, the first time we have had simultaneous measurements at 2 widely separated points on the heliospheric surface. And it reveals that the heliosphere is not a simple symmetrical bubble. It has structure. It has directionality. The direction from which the interstellar medium is flowing past the heliosphere, the local interstellar flow direction, creates a compressed nose on one side and an extended tail on the other, and the properties at the boundary differ depending on where you sample. This is valuable science that would have been impossible with a single spacecraft. The twin nature of the Voyager mission, 2 spacecraft sent in different directions, both achieving interstellar space, provides a kind of data that will not be repeated until another dedicated interstellar mission reaches the heliopause, which on current projections is decades away at minimum. The joint scientific legacy of the 2 Voyagers is therefore greater than either alone. Together, they have provided the first ever comparison of interstellar medium properties at 2 separate points. A sample size of 2 which is not impressive by statistical standards, but infinitely better than the sample size of 0 that preceded them. Let us now talk about something more concrete and more immediate, about what Voyager 1 has actually measured in the years since it crossed the heliopause in 2012, and how our understanding of interstellar space has changed as a result. Before Voyager 1 crossed the heliopause, all knowledge of the interstellar medium came from remote sensing, spectroscopy of starlight passing through interstellar gas, measurements of radio emissions from interstellar clouds, observations of how interstellar dust absorbs and scatters light. These techniques are powerful but indirect. They measure the integrated properties of material along a line of sight, not the local properties at a specific point. Voyager 1 provided the first in situ measurements made at the actual location with instruments physically present in the material being measured. This is qualitatively different from remote sensing, in the same way that a weather station on a mountain top gives different information from a satellite photograph of the mountain. What Voyager has measured since 2012 includes several findings that were not fully expected. The density of plasma in the local interstellar medium is higher than many models predicted. The electron density, measured by Voyager Using plasma wave observations, which infer electron density from the frequency of plasma oscillations produced by solar activity events, suggests a local interstellar electron density of about 0.06 to 0.13 electrons per cubic centimetre. This is at the upper end of what most models predicted, and has implications for understanding the structure of the local interstellar cloud. The magnetic field direction in the local interstellar medium is roughly consistent with predictions from remote sensing observations, but its magnitude is not perfectly constrained. There is still uncertainty in exactly how strong the local interstellar magnetic field is. Voyager's measurements provide a local data point, but the instrument that would directly measure the magnetic field strength, the magnetometer, has degraded over the decades in a way that makes absolute calibration difficult. Solar events propagate into interstellar space in a detectable way. Large solar storms, coronal mass ejections, solar energetic particle events send pressure waves outward through the heliosphere and beyond. Voyager has detected several of these events propagating past its location in interstellar space, appearing as brief increases in plasma density and pressure. This provides a real-time connection between solar activity and the interstellar medium. The Sun is not as isolated from its surrounding interstellar environment as once thought. The boundary between the heliosphere and the interstellar medium, the heliopause, appears to be not a static surface but a dynamic one. Evidence suggests it moves inward and outward by significant distances in response to changes in solar wind pressure and interstellar pressure. Voyager's observations over 12 years of interstellar travel are building up a picture of this dynamic boundary, a picture that will take years more of analysis to fully interpret. Each of these findings represents genuinely new knowledge, things we did not know and could not have determined without a spacecraft physically present in interstellar space. This is the scientific legacy of Voyager's longevity. Not just the planetary encounter science from the 1970s and 1980s, remarkable as that was, but the interstellar medium science that could only happen because the spacecraft survived long enough to reach interstellar space and continue functioning there. Let us now talk about the specific poignancy of the current situation, about what it means that we have right now something in interstellar space that is about to go silent. The transition from active science to silence will not be a sharp event. The power output of the RTGs declines gradually. The engineering team has been managing this decline for decades, carefully turning off heaters, consolidating functions, finding ways to maintain the most critical systems with ever-decreasing available power. Each decision to turn something off is irreversible. Once a heater is turned off in the cold of interstellar space, the component it was protecting may freeze permanently. The process of managing Voyager's declining power is a story of extraordinary resourcefulness. In 2023, engineers found that one of the redundant thrusters used for attitude control had a clogged fuel line, the first clog in the thruster's 45-year history. By activating a set of backup thrusters that had not been used since 1980, over 40 years of dormancy, they successfully restored attitude control without having to consume additional power for primary thruster heating. This kind of creative problem solving at a distance of 24 billion kilometers with 1970s hardware, using a team none of whom were alive when the spacecraft was designed, is genuinely remarkable. But there is a hard limit approaching. The RTGs will produce less and less power with each passing year. The point at which there is insufficient power to maintain the transmitter and the minimum required heating systems is a matter of years away, not decades. When the final signal arrives at Earth, it will have travelled 24 hours or more at the speed of light. It will be received by one of the Deep Space Network antennas, decoded, recorded, and then there will be nothing more from Voyager 1. The engineers who receive that final signal will know it is the last, or will know soon after when the expected next signal does not come. Some of them will have spent their entire careers working with this spacecraft. Some of them were children when it was launched. The final signal will be a moment of both scientific closure and personal loss. The end of a relationship between people and a machine that spans nearly a human lifetime. After that, silence from Earth's side. Voyager continues, but we no longer hear it. This makes the current moment, right now, as you listen to this, a moment of particular significance. The window when we can actually receive data from the first interstellar probe is open. It is closing. Every day it remains open is a day of irreplaceable scientific measurement. If you have access to the internet, you can look up the current status of Voyager 1 on NASA's Jet Propulsion Laboratory website. You can see its current distance, its current speed, its power output, the status of its instruments. These numbers update in real time. The distance grows by roughly 1.5 million kilometers per day. The power output decreases by a fraction of a watt per year. These numbers are real. They describe a real object doing a real thing right now. Let us now talk about the broader context of interstellar exploration, about what comes after Voyager and what the long-term strategy for understanding interstellar space might look like. Voyager reached the heliopause not because it was designed to, but because it survived long enough and had sufficient velocity to get there. Its velocity came from the gravitational assists, the planned series of planetary flybys that use Jupiter and Saturn's gravity to accelerate it well beyond solar escape velocity. This trajectory required a specific planetary alignment that occurs approximately every 175 years, the so-called Grand Tour alignment that exists only in the late 1970s. A dedicated interstellar probe, one designed from the beginning to reach and study interstellar space as its primary mission, would not need to wait for planetary alignments. It could use the Sun itself as a gravitational lens. A spacecraft flying very close to the Sun, within the orbit of Mercury at a few solar radii, and then firing its engine at the point of closest approach, takes maximum advantage of the Obert effect, the increase in propulsion efficiency when burning fuel deep in a gravity well. Such a solar Obert maneuver could potentially accelerate a spacecraft to 20, 30, or even higher multiples of Voyager's current speed. A spacecraft launched on a solar Obert trajectory could reach 100 astronomical units, Voyager's current distance, in a few years rather than 47. Concepts for such a mission have been studied. The interstellar probe concept, developed at Johns Hopkins Applied Physics Laboratory in the early 2020s, submitted to the Planetary Science Decadal Survey, proposed a spacecraft that could reach 1,000 astronomical units within 50 years using a solar Obert maneuver. At 1,000 astronomical units, the spacecraft would be deep into the unexplored outer heliosphere and beyond, sampling the interstellar medium at distances 10 times farther than Voyager has reached. This mission concept was not approved for implementation. It competed with other priorities, and the funding environment for a 50-year mission is challenging. But it represents the kind of thinking being done about the next step beyond Voyager. Further beyond this, the breakthrough starshot concept, laser-pushed light sails accelerated to 20% of the speed of light, represents a potential capability to reach Alpha Centauri in 20 years, Proxima b in 20 years, any of the nearby stellar systems within a human career. These light sails would be tiny, gram scale, and would carry minimal instrumentation. They would fly through rather than orbit, but they would provide the first ever close-up observations of another stellar system within a human lifetime. Whether breakthrough Starshot's engineering challenges are solvable, the laser array power requirements, the sail reflectivity, the miniaturized electronics, is uncertain. But the concept is physically plausible. The physics does not forbid it. Between Interstellar Probe and Breakthrough Starshot lies a space of possible missions, faster than Voyager, slower than light-sail interstellar probes, that could systematically explore the outer heliosphere and near interstellar space in ways Voyager never could. This is the scientific frontier that Voyager opened. Voyager showed us that the outer solar system and the interstellar medium can be reached, sampled, and studied by instruments we are capable of building. It demonstrated that the technical and institutional challenges of a multi-decade mission are surmountable. It created an expectation, a baseline, that other spacecraft can be built to reach interstellar space. That expectation is Voyager's longest-lasting legacy for the practice of science. Not the specific measurements it made, important as those are, but the demonstration that this kind of measurement is possible, that we can go there, that we can hear what is there, that the darkness between the stars is not inaccessible. Let us now talk about one more thing, about the specific nature of the knowledge that Voyager represents at the trillion-year scale, and why it matters that it was made at all. In 1 trillion years there will be, if anything resembling observers exists, nothing to indicate that Earth existed. The planet will be gone. The sun will be a cold, dead remnant. Every geological record of life on Earth will have been destroyed. Every artifact on Earth's surface will have been vaporized when the sun expanded. Every book, every building, every mountain, every ocean bed, gone. The only physical traces of humanity's existence that could persist on trillion-year timescales are objects that left Earth with sufficient velocity to escape the eventual death of the Sun. Objects that reached escape velocity and departed the solar system. Of these objects, Voyager 1 is the fastest, the farthest, and the most certain to be still moving through space in 1 trillion years. It is not inconceivable, though it is vanishingly improbable, that Voyager 1 could be discovered in 1 trillion years by some form of intelligence capable of physical investigation of the objects it encounters. If so, that intelligence would find a collection of atoms bearing isotopic signatures of a solar origin, a specific elemental composition pointing to formation in a specific type of stellar system. It would find metallic materials bearing the radiation damage signature of 1 trillion years in space. It might find traces of the original structure, enough to suggest the object was once manufactured by a technological process rather than naturally formed. And it might find, if it looked carefully enough with sufficiently advanced instruments, the chemical traces of plutonium decay products, evidence that the object once contained an artificial nuclear energy source, something no natural process produces, an unambiguous signature of technological origin. This would be evidence, not proof, but evidence, that beings capable of creating nuclear technology once existed somewhere in this part of the galaxy. Beings who also apparently had the capacity to launch objects into interstellar space. This is not a message in the ordinary sense. It is not the Golden Record's intended communication. It is a more primitive, more durable, more physical kind of signal. The signal that a technological civilization leaves in the universe simply by existing and by building things and by following the laws of physics that require those things to continue moving once launched. We did not design Voyager to leave this signal on trillion-year timescales. We designed it to study Jupiter and Saturn, and then we designed it to reach interstellar space, and we designed it to carry a message in the form of the Golden Record. All of those intentions are already fulfilled or will be in the near term. What happens in 1 trillion years is not our design, it is physics. The physics of conservation of momentum applied to an object in nearly empty space. We understood this physics, we applied it, and the result follows from that understanding in ways that go far beyond anything we consciously intended. This is one of the most important things about knowledge of physical law. When you truly understand a physical law and act in accordance with it, the consequences extend beyond your intentions, beyond your lifetime, beyond your civilization's lifetime, beyond your planet's lifetime. We understood that objects in motion tend to stay in motion in the absence of external forces. We applied that understanding to launch Voyager 1, and 1 trillion years from now, the consequence of our understanding will still be playing out, in the motion of atoms through the darkness of an aging universe. That connection between human understanding in 1977 and atoms in motion in 1 trillion years is Voyager's deepest meaning. Not the planetary images, not the golden record, not the interstellar medium measurements. The connection itself. The unbroken chain from our understanding to the physical consequence of that understanding playing out across 1 trillion years of time. We are at the beginning of that chain. The chain continues. Let us talk about something we have not yet examined carefully, about the specific experience of the people who work with Voyager right now, and what it is like to be responsible for an object that is simultaneously the farthest human-made thing in existence and one of the most aged and fragile. The Voyager mission is operated out of JPL, the Jet Propulsion Laboratory, in Pasadena, California. The team that manages the spacecraft is small by the standards of current major space missions. Many of the people who work on Voyager today were not born when it was launched. They have inherited the mission the way one inherits a complex piece of machinery from a previous generation, with documentation and institutional knowledge, but also with systems they did not design and anomalies they cannot fully explain. The 1977-era computers aboard Voyager use an instruction set that is essentially obsolete. The engineers communicating with the spacecraft must understand how to program these systems in languages and architectures that were current in the late 1970s. Some of the documentation from the original mission has been lost or degraded. Some institutional knowledge died with the original team members who have passed away in the decades since launch. This creates a situation where working with Voyager requires not only modern aerospace engineering skills, but also something like archaeology, the recovery and interpretation of old systems from fragmentary records. When the 2023 memory corruption problem occurred, part of the challenge was understanding exactly how the flight data system's memory was organized and what code was stored where. Knowledge that was not all perfectly preserved in the documentation. The communication cadence with Voyager is unlike anything in normal spacecraft operations. Most modern missions to Mars, to the outer planets, to Earth orbit, operate with communication delays that allow something resembling a conversation. A problem is detected, a response is formulated, the response is sent, the confirmation arrives. The cycle takes hours to days. For Voyager, each round trip takes about 44 to 46 hours. A question sent now gets its answer in almost 2 days. This means that the relationship with Voyager is fundamentally different from the relationship with any other active spacecraft. It is less like operating a remote vehicle and more like corresponding by mail with someone on the other side of the world, in the era before email. You write a letter, it travels, it arrives, a reply is composed, that reply travels, you receive it. The whole exchange takes days. Within this constraint, the engineers have found ways to work effectively. Procedures are tested extensively in simulation on Earth before being sent to the spacecraft. Commands are verified by redundant checking processes before transmission. The 44-hour wait for confirmation of any action requires a kind of patience and thoroughness that normal, faster-paced spacecraft operations do not demand. If you send the wrong command, you will not know it was wrong for almost 2 days, and you cannot easily undo it. This discipline, the requirement for extreme caution and thorough verification before any action, has served the mission well. Voyager has survived nearly 50 years, largely because the engineering team has been extraordinarily careful with what they ask it to do. The power budget management is particularly striking. In the early mission, the spacecraft had ample power. The RTGs were producing their full output, and there was comfortable margin for all systems. Over the decades, the team has made a long sequence of decisions about what to turn off, what to sacrifice to preserve what. Heaters for instruments that were no longer functioning scientifically were turned off to save power for the transmitter. Data rates were reduced to reduce the power required for transmission. The attitude control system was optimized to use thrusters less frequently. Every one of these decisions is permanent. You cannot turn a heater back on if the instrument it was protecting has frozen solid and the heater circuit itself has failed. You cannot recover a science instrument whose bearings seized when its lubricant froze. The slow sacrifices of Voyager systems over the decades are irreversible. Each one made the remaining systems more sustainable, but at the cost of capabilities that could never be recovered. This is a very particular kind of stewardship. The engineers managing Voyager today are not trying to restore it to its original capabilities. That is impossible. They are trying to keep the remaining functional systems alive for as long as possible, accepting permanent losses along the way, always balancing what they still have against what they can no longer afford to power. It is a form of management that has no good analogy in normal engineering. It is more like the care of a very elderly patient, where the goal is not recovery, but the preservation of quality of function for as long as possible, accepting that each intervention carries the risk of permanent loss. Let us now talk about the specific significance of the location Voyager currently occupies, about what it means physically to be in the region between the heliopause and the nearest stars, a region that has a specific name and specific properties that Voyager is uniquely positioned to measure. The region Voyager currently occupies is called the Very Local Interstellar Medium, the VLISM. This is the material immediately surrounding our solar system, the gas and dust and magnetic field within a few hundred light-years of the Sun. It is distinct from the general interstellar medium of the galaxy because it has been shaped by the specific history of this region, by supernova explosions in the recent astronomical past, by the motion of the Sun through various interstellar structures over the past few million years. We are currently moving through a structure called the Local Interstellar Cloud, a relatively warm, dense patch of interstellar gas that envelops the solar system and extends for perhaps 10 to 30 light-years in diameter. This cloud is itself embedded within a larger structure called the Local Bubble, a vast region of hot, tenuous gas roughly 300 light-years across, created by a series of supernova explosions in the Scorpius-Centaurus star-forming region over the past 10 to 20 million years. The supernova blast waves swept the surrounding gas outward, creating the hot cavity we now inhabit. This is the cosmic neighborhood context of Voyager's journey. It launched from the third planet of the Sun, crossed the heliosphere, exited into the local interstellar cloud, and is now sampling the material of that cloud directly. In a few thousand years, after Voyager's transmitter has long since gone silent, the spacecraft will exit the local interstellar cloud and enter the transition zone between it and the next interstellar structure. This transition will never be measured by Voyager. we will have lost contact long before it occurs. But the knowledge that such transitions exist and that Voyager will eventually cross them adds another layer to the understanding of what the spacecraft is journeying through. The local bubble itself, the hot, tenuous region surrounding us, has boundaries. Eventually, Voyager's atoms will cross those boundaries into the denser material of the inter-arm region of the galaxy. This crossing is billions of years in the future. The inter-arm region is denser in gas and dust, with different magnetic field properties, different cosmic ray flux. The journey continues through changing environments even after the atoms of Voyager lose all physical connection to their original structure. Let us now talk about something that is both scientifically significant and philosophically striking, about what the existence of Voyager in interstellar space tells us about the relationship between the solar system and the rest of the galaxy. For most of human history, the stars were thought of as fixed points on a celestial sphere, a backdrop against which the planets moved. The idea that the stars themselves were moving, that the sun was moving, that the solar system was hurtling through the galaxy at 220 kilometers per second was not established until the 19th century, and the full realization of what this movement means for our cosmic situation took even longer to absorb. The sun's motion through the galaxy means that the solar neighborhood is not a fixed address. The stars that are our nearest neighbors today are not the same stars that were our nearest neighbors millions of years ago, and they will not be our nearest neighbors millions of years in the future. Stars approach, pass by, and recede on timescales of millions to tens of millions of years. The stellar environment of the solar system changes continuously. This has implications for life on Earth that are just beginning to be understood. The passage of the solar system through regions of higher or lower star density, through spiral arms with their higher concentrations of massive stars and molecular clouds, through regions with different rates of supernova explosions, all of these affect the cosmic ray flux reaching Earth, the rate of comet bombardment from disturbances to the Oort cloud, and potentially the climate and biosphere on million-year timescales. Voyager 1, by crossing the heliopause and entering the interstellar medium, gave us our first direct measurements of the material through which the solar system is currently passing. We can now say with some precision what the density, temperature, and magnetic field of our current interstellar environment are. This is knowledge that matters for understanding the context of life on Earth. The local cosmic environment is not static but dynamic, and understanding it requires in situ measurement. In this sense, Voyager is not just exploring beyond the solar system. It is sampling the environment that the solar system inhabits. It is telling us where we are, cosmically, not just in terms of galactic coordinates, but in terms of the physical material that surrounds us right now. This is knowledge that before Voyager we had only from remote sensing, indirect, integrated, uncertain. Now we have it from direct measurement. It is one of the most concrete scientific contributions of the Voyager interstellar phase, making the local interstellar medium accessible to direct investigation for the first time. Let us now talk about one more layer to the trillion-year story, about what happens in the universe as a whole on timescales that dwarf even 1 trillion years, and how Voyager's atoms fit into the very long-term cosmic picture. Beyond 1 trillion years, the universe enters what physicists call the degenerate era, the period when all normal stars are dead and the dominant objects are stellar remnants. White dwarfs, the cooling remnants of sun-like stars, cool extremely slowly. In the current universe, the oldest white dwarfs are still quite warm, a few thousand Kelvin, because the universe is not yet old enough for them to have cooled significantly. In a few trillion years, the oldest white dwarfs will have cooled to black dwarfs, cold, dark objects maintained by electron degeneracy pressure, no longer radiating significant heat or light. The transition from white dwarf to black dwarf takes longer than the current age of the universe. In a trillion years, the coolest white dwarfs are just beginning this transition, still faintly glowing, still radiating feeble heat, but progressively fading. In 10 to the 14th power years, 100 trillion years, all main sequence stars are dead. The universe is populated by black dwarfs, neutron stars, black holes, and possibly the last dying remnants of the most ancient red dwarfs. In 10 to the power of 19 to 10 to the power of 20 years, 10 billion years, an important process begins to matter. Gravitational interactions between stellar remnants cause some to be ejected from galaxies entirely, while others sink toward the galactic center. Over these timescales, galactic structure slowly dissolves. The organized shapes of spiral and elliptical galaxies give way to diffuse clouds of stellar remnants with a dense concentration of material near the central black hole. In 10 to the power of 37 to 10 to the power of 100 years, depending on which theoretical models are correct, proton decay either occurs or does not. If protons decay, the matter composing stellar remnants, including black dwarfs and neutron stars, slowly evaporates as the protons that make up atomic nuclei spontaneously transform into positrons and other particles. The result is an era in which even the most stable forms of matter gradually dissolve into radiation and elementary particles. If protons are stable, if they never decay regardless of timescale, then matter persists indefinitely. Black dwarfs and neutron stars endure for timescales that exceed anything calculable. The universe's ultimate fate in this scenario is a state of maximum entropy, a vast cold expanse in which the remaining matter is spread to maximum uniformity and no process capable of extracting useful work from energy differentials remains possible. Voyager's atoms in the context of these scenarios. If proton decay occurs in the 10 to the 37th to 10 to the 45th year range, the atoms of Voyager are gone by this timescale, their constituent protons and neutrons transformed into lighter particles and radiation. The trillion-year journey of the atoms ends in the fire of proton decay. If proton decay does not occur, the atoms persist indefinitely. They continue drifting through a universe in which all stars are dead, all galaxies have dissolved or collapsed, all organized structure has faded. They are part of the diffuse background of matter spread across an unimaginably vast volume of space, contributing negligibly to the universe's total matter content, but physically present and still moving. In either case, the question of whether Voyager's atoms are still meaningfully Voyager is long since answered. No. Even in the scenario where the atoms persist, they have been dispersed across light years or larger distances by the accumulated gravitational and mechanical interactions of a trillion years. There is no unified object. There is no golden record. There is no spacecraft. There are atoms, moving in different directions through a universe that has forgotten almost everything that once existed in it. The law of conservation of momentum continues to apply to each one individually. Each atom moves in a straight line, or close to it, deflected occasionally by rare gravitational interactions with whatever other matter it encounters, until acted upon by an external force. The external forces in the very late universe are vanishingly rare. Matter is spread so thinly that atoms rarely encounter each other. In the post-stellar universe, the atoms of Voyager move essentially without hindrance, travelling in their individual directions essentially forever. This is the final state of Voyager's journey. Not a place, but a condition. Individual atoms, each moving in its own direction, each carrying in its nuclear structure the isotopic history of a solar system that no longer exists, each having travelled for a time that no word in human language adequately describes. They do not know they were once Voyager. They do not know they were once part of something that travelled from a planet around a star in a galaxy that no longer exists as a recognisable structure. They are atoms. They do what atoms do. They continue. And in this continuation, pointless by any measure of human meaning, inescapable by the measure of physical law, there is something that is genuinely difficult to name. Not beauty exactly, not tragedy exactly, not comfort exactly. Something that does not fit any of the standard categories of emotional response. The feeling of standing at the edge of what language can describe and looking outward. The feeling you get when you hold in your mind simultaneously that Voyager is right now 160 astronomical units from Earth, sending a 22-watt signal that we're receiving, and that its atoms will be moving through the darkness of an empty universe 1 trillion years from now, and that both of these facts follow from the same physical laws, and neither of them is more or less real than the other. Both are true, at the same time, in the same universe. The spacecraft sending its signal right now, the atoms drifting in darkness 1 trillion years from now. These are not two different Voyagers. They are the same continuous physical reality at two different moments of its long trajectory through time. And we, right now, are watching the beginning of that trajectory. The signal still comes in, the numbers still update, the distance still grows by 1.5 million kilometers per day. We are here at the moment when the journey can still be heard. That moment is closing, but it has not closed yet. Let us talk about one more thing that deserves attention, about the specific relationship between Voyager's journey and the human experience of time. Because this is perhaps the most intimate connection between what Voyager is doing physically and what we're doing psychologically when we think about it. We experience time in a very particular way. We live in a present that moves, always forward, always at the same rate, always carrying us from what was to what will be. Our memories reach back decades. Our planning reaches forward years or decades at most. The scale of a human life, roughly a century at the generous end, is the temporal frame within which almost all meaningful human experience occurs. Voyager 1 was launched in a specific year, 1977. People alive today have a personal relationship with that year. Some were born then, some were children. Some were adults watching the launch on television. The year 1977 is within the living memory of hundreds of millions of people, and the spacecraft launched in that year is right now in interstellar space. The connection between 1977, a year people remember personally, and interstellar space, a realm that feels abstract and distant, is bridged by a continuous physical object. Voyager has been moving continuously since September 5th, 1977. Every moment between that launch and this moment is part of its trajectory. There is no gap, there is no discontinuity. The same physical object that left Earth 47 years ago is the same physical object now in interstellar space. This continuity is one of the most psychologically striking things about Voyager. It is not the result of an instantaneous jump to a distant location. It got there by travelling continuously, 1 second at a time, for 47 years. Every second of those 47 years is part of its journey. The journey is built from seconds in exactly the way our lives are built from seconds. And now those seconds are running out. Not for the journey, which continues, but for the communication. The transmitter is fading. The power is declining. The remaining operational life of Voyager's electronics is measured in years. When Voyager finally goes silent, it will be like the last fading of a voice that has been speaking continuously since 1977. Not abrupt, not dramatic, just quieter and quieter until one day there is nothing more. A voice that has been speaking for nearly 50 years, telling us what it has found in a place no other human instrument has been. And then, silence. The journey continues in that silence. Unchanged by the silence. Indifferent to the silence. That is Voyager. Go outside tonight. Find a dark place. Let your eyes adapt. Then look in the direction of Ophiuchus. In summer it rises high in the southern sky, a constellation without a distinctive pattern, easy to overlook. Somewhere in that direction, 160 astronomical units away, 24 billion kilometers through the darkness of interstellar space, Voyager 1 is moving. You cannot see it. No telescope on Earth can see it. It is too small and too dark. You see only the sky, empty by human standards, unimaginably populated by astronomical ones. But it is there. Right now, while you stand outside looking up, its 22-watt transmitter is sending a signal through 24 billion kilometers. In roughly 22 hours, that signal will arrive at a 70-meter antenna somewhere on Earth. In Goldstone, in Madrid, in Canberra. Engineers will receive it. Data about the interstellar medium, the density of plasma, the direction of magnetic fields, the flux of cosmic rays, will be recorded. This is happening now, not as an abstraction, as a physical process occurring at this moment in the universe you inhabit. Here is what Voyager 1 is, physically. A metal object weighing 722 kilograms, about 2 meters across. Computers with less processing power than a calculator. RTGs producing roughly 240 watts, slightly more than 2 old incandescent bulbs. A gold-plated disc with grooves encoding the sounds of rain, children laughing, bark, Chuck Berry, the surf, birdsong, greetings in 55 languages. And here is what its journey amounts to. In 40,000 years it will pass within 1.7 light-years of a red dwarf called AC plus 793888. Nothing dramatic will happen. A gentle gravitational nudge, a trajectory imperceptibly deflected. By the time this occurs, every human civilization currently existing will be as distant in time from that moment as ancient cave painters are from us. In 1 million years, it will be 17 light-years from the Sun. Its structure will be showing radiation damage accumulated over 1 million years of cosmic ray bombardment, but its atoms intact. Gold remains gold. Aluminium remains aluminium. The journey continues. In 1 billion years, its atoms will be scattered over perhaps kilometers of space, the unified spacecraft long since fragmented by 1 billion years of accumulated damage. No longer recognizable as a single object, but every atom still moving, still carrying in its nuclear structure the isotopic signature of its origin in a solar system that is by now profoundly changed. The Sun 1 billion years brighter, Earth perhaps no longer habitable. In 5 billion years, the atoms that were Voyager are 75,000 light-years from the place the Sun used to be when they were launched. The Sun has expanded into a red giant and contracted to a white dwarf. Earth is gone, or burned beyond recognition. Whatever became of humanity has either survived in some form beyond Earth or ended. The atoms drift through the merged galaxy of Milkomeda, the combined structure of the Milky Way and Andromeda, long since completed their 4 billion year collision. In 1 trillion years. The universe is 72 times older than it is now. Almost all stars are dead. New ones are no longer forming. The gas ran out trillions of years ago. Space is populated by slowly cooling white dwarfs, neutron stars, black holes, and the last fading embers of the smallest red dwarfs. The observable universe for any hypothetical observer in our galaxy is nearly empty. Dark energy has carried almost every other galaxy beyond the horizon of light-speed communication. And somewhere, perhaps 17 million light-years from where the sun used to shine, perhaps farther if gravitational scatterings ejected them into intergalactic space, atoms drift. Atoms of aluminium and gold and platinum and titanium, separated from each other perhaps by light-years, bearing in their nuclear structures the isotopic signature of a solar origin, bearing the radiation damage of 1 trillion years in space. They were never stopped. From September 5th, 1977 to 1 trillion years later, not one moment of stillness. Moving always, through the heliosphere, through the local interstellar cloud, through whatever lies beyond, through the collision of 2 galaxies, through the death of stars, through the slow cooling of the universe toward its final state. The law of conservation of momentum is absolute. In interstellar and intergalactic space, there is essentially nothing to stop them. They will continue until the universe itself changes in ways that make motion meaningless, until proton decay dissolves them, or until the universe reaches its final thermodynamic state in which no energy gradient remains to power any process. This is what people did in 1977. With chemical rockets and 1970s computers and a 22-watt transmitter. They applied their understanding of physical law to an engineering problem and launched something that will outlast their civilization, their species, their planet, their star, and the recognizable structure of their galaxy. Not because they intended to outlast all those things, because conservation of momentum is true, and empty space is nearly empty, and those 2 facts together have consequences that extend to the end of time. Right now, its transmitter is still on. The signal still travels 22 billion kilometers to Earth. The engineers at JPL still receive it. The data still comes in. This will not last much longer. A few more years, perhaps to 2030, perhaps a little beyond. Then, silence. The journey will not end when the signal does. The journey has no end that physics can provide on any timescale we can meaningfully imagine. Only the communication ends. When you go back inside tonight, that signal will still be travelling. When you sleep, the signal will still be travelling. When you wake, the engineers will have received it and recorded it, and it will be part of the data archive of the first interstellar probe humanity ever built. And in 1 trillion years, the atoms will still be moving. From a refrigerator light bulb of transmitter power, a message through the darkness that outlasts everything.